Okay, so in this lesson, we're going to touch on functions and their graphs, and this is chapter 2 of linear equations and the functions. All right, so first we want to look at is what is a relation? Now, a relation is a mapping or pairing of input values with output values. The set of input values, we call that the domain or the independent variable. And as you will see, that's going to be represented by x values. And then we have the set of output values, which we will call the range, or our dependent variable, sorry. Okay, so our independent variable is the domain, is the input values, and our output values or the range is also known as the dependent variable. Now, what's important to note is what a relation is when it's a function, but we'll get to that in a moment. What we want to do now is just simply go over how functions and the graphs can be represented. There's different ways that you can represent a relation, and the first one is what we call a mapping diagram. Now, a mapping diagram is just simply a figure, an image that helps you to see how the transition works from the inputs to the outputs. So here you see we've now put here x and y, and so you can say input, domain, independent variable, or the x values. And they are mapped to the output values, which we see here is y, or as we heard earlier, the range or dependent variables. So you see 2 is mapped to 3, 5 is mapped to 3, -1 is mapped to -2, and 6 to -2. All right, so we can also represent them by tables. So we can take a table of values, and our x values, as you might have learned in Algebra 1, represent our domain, they represent the independent variable, they represent the input. And we can create, when we put them into an equation, we get out the output values, the dependent variable, the range of values. Then we have what's called graphs. We can represent the relations in a graphical form by plotting the points from the tables. And so we can represent them as a diagram, tables, and then into a graph. And then the graphs, as you remember in Algebra 1, or you should have learned it possibly, that you can write what the equation of the graph is. And we're going to learn about this really soon of what we call function notation. Generally, you see it as y equals to, but we're going to look into that a little bit more. And then last of all, verbal descriptions as we have with different types of proportions as we see here. Okay, so let's go ahead and look at what is a function. So when you take a relation, which is a mapping or pairing of those different values, it can be a function if and only if there is exactly one input for each output. What does that mean? Well, we have an example here using the mappings, then we're going to do one with tables and graphs. So let's look at the mapping first. So if we use the mapping diagram, first thing we want to do is just identify the domain and the range of each mapping, and then determine if these relations are functions or not using that definition above. All right, let's start off with the first one. We see here this is our input. And remember, our input values is also known as the domain. So you could write that down there on the side that the input is also the domain. So our domain values here are 2, 5, -1, and 6. And then our range of values are also known as the output or the y values, which is simply 3 and 2. All right, so let's determine whether or not this one is a function. Well, if we look at it carefully, we see the 2, 5, the -1, and the 6 are all being mapped to an output. And there is exactly one for each one. So is it an input or output? I mean, a function or not? Yes, this one is a function. Okay, how about the second one? The domain here is the input value. So 4, 3, 2, 1 is the domain, the input values, the independent variable. And our y values or our range or our output that was a little bit tricky, is 5, 6, 8, and 3. And so those are our range of values. And then we want to see if this is a function. Now this is where we put our thinking caps on and can use this to assist us. If we look carefully here, looking at that definition again, and we even go over the previous one, it says there has to be one input for each output. And so if you look at this one carefully, what you will see is that, I'm going to skip that first. We can write these relations as ordered pairs. So just to help you out, this will help us out in answering that question. We see here that we can say 2 and 3 makes this first coordinate pair. 5 and the 3 makes the second one. -1 and the 2 make the third, and 6 and 2 make the fourth. And that's because an ordered pair can be written in XY format, also known as a coordinate point. And the reason why we call them an ordered pair is because they are in order, alphabetical order. X comes before Y. And so that's how we can do it. So even here with the second one, if we put it into its terms of an ordered pair, we can really see whether or not it's a function. So let's start with the first one. 4 is mapped to 5, which means as a coordinate point, it's the coordinate 4, 5. The 3 can be mapped to the 6, which we get the coordinate 3, 6, or ordered pair 3, 6. But then notice there's nothing there for the 2, and then that 1, there's two coordinate points that start with the 1. So that means that there are two inputs. And remember, this says exactly one input. So that means it fails to be a function because of those two ones, which means if you're writing a set of coordinate points and you see two ones, or you see two arrows coming from the one in the mapping diagram or from that input, then you know it's not a function. It also fails here because this one does not have an output. There's one input, but there's no output to map to, and so it fails because of two reasons. And so this one here is not a function, simply because there are two arrows coming from the mapping. In its coordinate point form, there are two ones, and so therefore it does not satisfy what it means to be a function. All right, so let's go on a little bit more to see how we can represent this. Remember, coordinate points, we could take those, and because they're in the XY format, we can go ahead and put them into what we call a table. And so our points, if we put them in not alphabetical, sorry, in numerical order, we start with the first point, negative 1, 2, then the second one, 2, 3, and then the third, 5, 3 in order, and then 6, 2. Right? And so what we see is that if we were putting these into equations, the inputs, the x values, what we would get out from that would be what we call our output, our range of values, or a dependent variable. And that's the connection between the mapping diagram and the table. We could do the same with the second one, and you can see why it will not be a function with the table. If we try to put it in the table, this is what we will get. And if you've ever used a table before, you'll see this looks a bit strange, mainly because we have the two ones there. And the reason why we call it an independent variable, at least you can kind of conclude this, is that it's independent of itself. It's always continuous. So it has to have that pattern of 1, 2, 3, 4, 5 with no repetitions. And so when you see that, if you were to see a table like that, you would know automatically that that cannot be a function. So what would happen if we did it graphically? Remember, we talked about there's different representations, and that is one as a graph. Before we do that, let's just recap of what a graph looks like. Remember, in our Cartesian plane, what is also called the quadrant ones, they go in a counterclockwise direction, or rather the quadrants. Now, quadrant 1 is always in the top right corner, and we start off with the positive values. Remember, in terms of x, y, what we're saying here is that the x values will be positive, as you see in the blue line here. The x values will be positive, and also our y values will be positive, as you see here. And so that's basically how the quadrant works. Now, if we move on to the next quadrant in a counterclockwise direction, what we're going to see is how the values look there. What we see here is that the x values are now negative. So it will be negative x values, as you see on this side. And then the y values will be positive, as you see here. So all the different points are found by those two, as you might recall in Algebra 1. All right, now let's look at the third quadrant, once again going in a counterclockwise direction. What we see here is quadrant 3, they're both negatives. And I won't write and draw on the axis this time, but we would have negative x and negative y values as seen on those x and y values. And then the last quadrant, of course, quadrant 4, we see positive values in the x-axis and negative values in the y. And so all the points that will lie in this part of the quadrant, this section of the graph, will be of the form positive, negative. All right, so keep that in mind as we move on. So if we were to take now those tables that we had, remember we had those tables, these ones right here, and we were to plot them onto the graph, this is what it will look like. If we had those tables, we have the point negative 1, 2. We have 2, 3. You see the quadrants match the positive values. Quadrant 1 has all positive, and quadrant 2 has a negative positive. The third value would be here, and then the fourth here as well. And so basically what we're seeing there is how we can translate them onto a graph. The same with the second one. If we were to plot the points, you see that there's no point for 2, and where it failed, what we're going to see is how we can see whether something's a function when looking at a graph. Because it fails at 1, 3, and 1, 8, because the x values repeat, that means we should see some type of pattern that helps us to see whether or not it fails in the graph. And that's by taking a line. If you took a straight line, and that could be your finger, a ruler, your pen, and run it through a set of points or a graph, and that line touches 2 or more of the points, then that set of relations is not a function. If we test it on the other side and we run that straight line through there, you see it never touches those points at 2 different points on the line. And therefore, the first one is a function by the graph. And that's how we can test whether things are functions. Let's try it with a real graph, but here's the definition as seen in the textbook, page 68. And it says a relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. So for these two graphs, as you see in the prompt, determine if the graphs of these relations are functions or not. So let's try the first one. If we run a vertical line through there, you see it only touches that graph at one point as it goes through the entire graph. How about the second one? Well, with the second one, as it goes through, you see it can touch at multiple points. And so because of that, it could touch when that line goes through. It could touch here and here, here and here, here and here, right? When that line goes through it, what we'll see is basically that multiple times it can touch 2 points in 2 points it can touch, but at multiple times as the line passes through. And so that means that this one would not be a function. So yes, the first one's a function, but no, this one fails the vertical line test. So remember, if you have a mapping and you see 2 arrows come from the input values, it's not a function. If one of the input values is not mapped to the second and to the output values, then it's not a function. In the tables, if you see x values repeated, it's not a function. As coordinate points, if you see x values repeated, it's not a function. And if in a graph, using the vertical line test, it touches at multiple values, 2 or more x values, then it is not a function.